Hello everyone, this is Srijit and welcome to MCAC35 Advanced Database Management System. Last class we started special databases with the temporal data. Now let's see spatial and geographic data. First let's see spatial data. Spatial data support in database is important for efficiently storing, indexing, and querying of data on the basis of spatial locations. For example, suppose that we want to store a set of polygons in a database and query the database to find all polygons that intersect a given polygon. We cannot use standard index structures such as B-trees or hash indices to answer such a query efficiently. Efficient processing of the above query would require special purpose index structures such as R-trees for the task. Two types of spatial data are particularly important. First one is the computer-aided design or CAD data, which include spatial information about how objects such as buildings or vehicles are constructed. Other important examples of computer-aided design database are integrated circuit and electronic device layouts. Geographic data such as road maps, land usage maps, topographic elevation maps, political maps showing boundaries, land ownership maps, and so on. Geographic information systems are special purpose databases tailored for storing geographic data. Support for geographic data has been added to many database systems such as the IBM DB2 Spatial Extender, the Informix Spatial Data Blade, and Oracle Spatial. Now let's see the representation of geographic information. The figure listed how various geometric constructs can be represented in a database. In a normalized fashion, we stress here that geometric information can be represented in several different ways, only some of which we are going to describe here. A line segment can be represented by the coordinates of its endpoints. For example, in the map database, the two coordinates of a point would be its latitude and longitude. A polyline, also called a line string, consists of a connected sequence of line segments and can be represented by a list containing the coordinates of the endpoints of the segmenting sequence. We can approximately represent an arbitrary curve by polylines by partitioning the curve into a sequence of segments. This representation is useful for two-dimensional features such as roads. Here, the width of the road is small enough relative to the size of the full map that it can be considered to be a line. Some systems also support circular arcs as primitives, allowing curves to be represented as sequences of arcs. We can represent a polygon by listing its vertices in order. As in figure, the list of vertices specifies the boundary of a polygonal region. In an alternative representation, a polygon can be divided into a set of triangles as shown in the figure. This process is called triangulation, and any polygon can be triangulated. The complex polygon can be given an identifier, and each of the triangles into which it is divided carries the identifier of the polygon. Circles and ellipses can be represented by corresponding types or can be approximated by polygons. A list-based representation of polylines or polygons are often convenient for query processing. Such known-first normal form representations are used when supported by the underlying database, so that we can use fixed size tuples, first normal form, for representing these polylines. We can give a polyline or curve an identifier and can represent each segment as a separate tuple that also carries with it the identifier of the polyline or curve. Similarly, the triangulate representation of a polygon also allows a first normal form relational representation of polygons. The representation of points and line segments in three-dimensional space is similar to their representation in two-dimensional space. The only difference being that the points have an extra z components. Similarly, the representation of planar figures such as triangles, rectangles, and other polygons does not change much when we move to 3 dimensions. Tetrahedrons and cuboids can be represented in the same way as triangles and rectangles. We can represent arbitrary polyhedra by dividing them into tetrahedrons, just as we triangulate polygons. We can also represent them by listing their faces, each of which is itself a polygon, along with an indication of which side of the face is inside the polyhedron. Now let's see design databases. Computer-aided design or CAD systems traditionally store data in memory during editing or other processing and wrote the data back into the file or serialized it at the end of the session of editing. The drawbacks of such a scheme include the cost of, say, programming complexity as well as time cost of transforming data from one form to another, and the need to read in an entire file even if only part of them are required. For large designs, such as the design of a large-scale integrated circuit or the design of an entire airplane or an entire building, it may be impossible to hold the complete design in memory. The designers of object-oriented databases were motivated in large part by the database requirements of CAD systems. Object-oriented databases represent components of the design as objects, and the connections between the objects indicate how the design is structured. The objects stored in a design database are generally geometric objects. Simple two-dimensional geometric objects include points, lines, triangles, rectangles, and general polygons. Complex two-dimensional objects can be formed from the simple objects by means of a union or intersection operation, and as well as a difference operation. Similarly, complex three-dimensional objects can be formed from the simple objects such as spheres, cylinders, and cuboids by union, intersection, and difference operations, as is shown in the figure. Three-dimensional surface may also be represented by wireframe models, which essentially model the surface as a set of simpler objects such as line segments, triangles, and rectangles. Design databases also store non-spatial information about objects, such as the material from which the objects are constructed. We can usually model such information by standard data modeling techniques. Various spatial operations must be performed on a design. For instance, the designer may want to retrieve the part of the design that corresponds to a particular region of interest. Spatial index structures are useful for such tasks. Spatial index structures are multidimensional, dealing with two- and three-dimensional data rather than dealing with just a simple one-dimensional ordering provided by the B+ trees. Spatial integrity constraints such as two pipes should not be in the same location are important to design databases to prevent interference errors. Such errors often occur if the design is performed manually and are detected only when the prototype is being constructed. As a result, these errors can be expensive to fix. Database supports for spatial integrity constraints help people to avoid design errors, thereby keeping the design consistent. Implementing such integrity checks again depends on the availability of efficient multidimensional index structures. Now let's see geographic data. Geographic data are spatial in nature but differ from design data in certain ways. Maps and satellite images are typically examples of geographic data. Maps may provide not only location information about boundaries, rivers, and roads, for example, but also much more detailed information associated with the locations, such as elevation, soil type, land usage, and annual rainfall. Now see the representation of geographic data. Geographic data can be categorized into two types. First one is the raster data. Such data consists of bitmaps or pixel maps in 2 or 3 dimensions. A typical example of a two-dimensional raster image is a satellite image of an area. In addition to the actual image, the data includes the location of the image, specified, for example, by the latitude and longitude of its corners, and the resolution, specified either by the total number of pixels or more commonly in the context of geographic data by the area covered by each pixel. Raster data is often represented as tiles, each covering a fixed sized area. A larger area can be displayed by displaying all the tiles that overlap within the area. To allow the display of data at different zoom levels, a separate set of tiles is created for each zoom level. Once the zoom level is set by the user interface, for example in a web browser, tiles at that zoom level which overlap the area being displayed are retrieved and displayed. Raster data can be three-dimensional, for example, the temperature of different altitude at different regions, again measured with the help of a satellite. Time could form another dimension, for example, the surface temperature measurement at different points in time. Now see the second type, that is the vector data. Vector data are constructed from basic geometric objects such as points, line segments, polylines, triangles, and other polygons in 2 dimensions, and cylinders, spheres, cuboids, and other polyhedrons in 3 dimensions. In the context of geographic data, points are usually represented by latitude and longitude, and where the height is relevant, additionally by elevation. Map data are often represented in vector format. Roads are often represented as polylines. Geographic features such as large lakes or even political features such as states and countries are represented as complex polygons. Some features such as rivers may be represented either as a complex curve or as complex polygons, depending on whether their width is relevant. Geographic information related to regions such as annual rainfall can be represented as an array, that is, in raster form. For space efficiency, the array can be stored in a compressed form. We will study an alternative representative of such arrays by a data structure called a quadtree in later. As another alternative, we can represent a region information in vector form using polygons, where each polygon is a region within which the array value is the same. The vector representation is more compact than the raster representation in some applications. It is also more accurate for some tasks such as depicting roads, where dividing the region into pixels leads to a loss of precision in location information. However, the vector representation is unsuitable for applications where the data are intrinsically raster based, such as satellite images. Topographical information, that is information about the elevation or height of each point on a surface, can be represented in raster form. Alternatively, it can be represented in vector form by dividing the surface into polygons covering regions of approximately equal elevation, with a single elevation value associated with each polygon. As another alternative, the surface can be triangulated, that is, divided into triangles, with each triangle representing by an altitude, longitude, and elevation of each of its corners. The latter representation, called the triangulated irregular network or TIN representation, is a compact representation which is particularly useful for generating three-dimensional views of an area. Geographic information systems usually contain both raster and vector data and can merge the two kinds of data when displaying results to users. For example, maps associations usually contain both satellite images and vector data about roads, buildings, and other landmarks. A map display usually overlays different kinds of information. For example, road information can be overlaid on a background satellite image to create a hybrid display. In fact, a map typically consists of multiple layers which are displayed in bottom to top order. Data from higher layer appears on top of data from lower layers. It is also interesting to note that even information that is actually stored in vector form may be converted to raster form before it is sent to a user interface such as a web browser. One reason is that even web browsers that do not support scripting languages can then display map data. A second reason may be to prevent end users from extracting and using the vector data. Map services such as Google Maps and Yahoo or Bing Maps or Google Earth provides APIs that allow users to create specialized map displays containing application-specific data overlaid on top of standard map data. For example, a website may show a map of an area with information about restaurants overlaid on the map. The overlays can be constructed dynamically, displaying only restaurants with a specific cuisine, for example, or allowing users to change the zoom level or pan the display. The map APIs for a specific language, typically JavaScript or Flash, which is deprecated now, are built on top of a web service that provides the underlying map data. Now let's see the applications of geographic data. Geographic databases have a variety of uses, including online map services, vehicle navigation systems, distribution network information for public service utilities such as telephone, electric power, and water supply systems, and land usage information for ecologists and planners. Web-based road map services form a very widely used applications of map data. At the simplest level, these systems can be used to generate online road maps of a desired region. An important benefit of online maps is that it is easy to scale the maps to the desired size, that is, to zoom in and out to locate relevant features. Road map services also store information about roads and services, such as the layout of roads, speed limits on roads, road conditions, connections between roads, and one-way restrictions. With this additional information about roads, the maps can be used for getting directions to go from one place to another and for automatic trip planning. Users can query online information about services to locate, for example, hotels, gas stations, or restaurants with the desired offerings and price ranges. In recent years, several web-based map services have defined APIs that allow programmers to create customized maps that include data from the map services along with data from other sources. Such customized maps can be used to display, for example, houses available for sale or rent, or shops and restaurants in a particular area. Vehicle navigation systems are systems that are mounted in automobiles and provide road maps and trip planning services. They include a global positioning system or GPS unit, which uses information broadcast from GPS satellites to find the current location with an accuracy of tens of meters. With such a system, a driver can never get lost. The GPS unit finds the location in terms of latitude, longitude, and elevation, and the navigation system can query the geographic database to find where and on which road the vehicle is currently located. Geographic databases for public utility information have become very important as the network of buried cables and pipes has grown. Without detailed maps, work carried out by one utility may damage the cables of another utility, resulting in large-scale disruption of services. Geographic databases coupled with accurate location finding systems help avoid such problems. Next, let's see spatial queries. There are a number of types of queries that involve spatial locations. Nearness queries request objects that lie near a specified location. A query to find all restaurants that lie within a given distance of a given point is an example of a nearness query. The nearest neighbor query requests the object that is nearest to the specified point. For example, we may want to find the nearest gasoline station or a hotel. Note that this query does not have to specify a limit to the distance, and hence we can ask even if we have no idea how far the nearest gasoline station lies. Then we have region queries deals with the spatial region. Such a query can ask for objects that lie partially or fully inside a specified region. A query to find all retail shops within a geographic boundary of a given town is an example for region query. Queries may also request intersections and unions of regions. For example, given region information such as annual rainfall and population density, a query may request all regions with a low annual rainfall as well as a high population density. Queries that compute intersections of regions can be thought of when computing the spatial join of two spatial relations. For example, one representing rainfall and the other representing the population density, with the location playing the role of a joining attribute. In general, given two relations, each containing spatial objects, the spatial join of the two relations generate either pairs of objects that intersect or the intersection regions of such pairs. Several join algorithms efficiently compute spatial joins on vector data, although nested loop join and indexed nested loop join with the spatial indices can be used. Hash joins and sort merge joins cannot be used in spatial data. Researchers have proposed join techniques based on coordinate traversal or spatial index structures on the two relations. In general, queries on spatial data may have a combination of spatial and non-spatial requirements. For instance, we may want to find the nearest restaurant that has vegetarian selections and that charges less than $10 for a meal. Since spatial data are inherently graphical, we usually query them by using a graphical query language. Results of such query are also graphically displayed rather than in tables. The user can invoke various operations on the interface, such as choosing an area to be viewed, for example by pointing and clicking on suburbs west of Manhattan, zooming in and out, choosing what to display on the basis of selection conditions, for example houses with more than 3 bedrooms, overlay of multiple maps, for example houses with more than 3 bedrooms overlaid on a map showing areas with low crime rates, and so on. The graphical interface constitutes the front end. Extensions of SQL have been proposed to permit relational database to store and retrieve spatial information efficiently, and also to allow queries to mix spatial and non-spatial conditions. Extensions include allowing abstract data types such as lines, polygons, and bitmaps, and allowing spatial conditions such as contains or overlaps. Next, let's see indexing of spatial data. Indices are required for efficient access to spatial data. Traditional index structures such as a hash indices and B trees are not suitable since they deal only with one-dimensional data, whereas spatial data are typically of two or more dimensions. Let's see the KD trees. To understand how to index spatial data consisting of two or more dimensions, we consider first the indexing of points in one-dimensional data. Tree structures such as binary trees and B trees operate by successively dividing space into smaller parts. For instance, each internal node of a binary tree partitions a one-dimensional interval into points that lie in the left partition go into the left subtree, points that lie in the right partition go into the right subtree. In a balanced binary tree, the partition is chosen so that approximately one half of the points stored in the subtree fall in each partition. Similarly, each level of a B tree splits a one-dimensional interval into multiple parts. We can use this intuition to create tree structures for two-dimensional space as well as in higher dimensional spaces. A tree structure called a KD tree was one of the early structures used for indexing in multiple dimensions. Each level of a KD tree partitions the space into two. The partitioning is done along one dimension at the node at the top level of the tree, along another dimension in nodes at the next level, and so on, cycling through the dimensions. The partitioning proceeds in such a way that at each node approximately one half of the points stored in the subtree falls on one side and one half falls on the other. Partitioning stops when the node has less than a given maximum number of points. The figure shows a set of points in two-dimensional space and a KD tree representation of the set of points. Each line corresponds to a node in the tree and the maximum number of points in the leaf node has been set at 1. Each line in the figure, other than the outside box, corresponds to a node in the KD tree. The numbering of the lines in the figure indicates the level of the tree at which the corresponding node appears. The KDB tree extends the KD tree to allow multiple child nodes for each internal node, just as a B tree extends a binary tree to reduce the height of the tree. KDB trees are better suited for secondary storage than KD trees. Next, let's see quad trees. An alternative representation for two-dimensional data is a quad tree. An example of the division of space by a quad tree appears in the following figure. The set of points is the same as that in the previous figure. Each node of a quad tree is associated with a rectangular region of space. The top node is associated with the entire target space. Each non-leaf node in a quad tree divides its region into 4 equal-sized quadrants, and correspondingly each such node has 4 child nodes corresponding to the 4 quadrants. Leaf nodes have between 0 and some fixed maximum number of points. Correspondingly, if the region corresponding to the node has more than the maximum number of points, child nodes are created for that node. In the example on the figure, the maximum number of points in the leaf node is set to 1. This type of quadtree is called a PR quadtree to indicate it stores points and that the division of space is divided based on regions rather than on the actual set of points stored. We can use region quadtrees to store array, which is of raster type information. A node in a region quadtree is a leaf node if all the array values in the region that it covers are the same. Otherwise, it is subdivided further into 4 children of equal area and is therefore an internal node. Each node in the region quadtree corresponds to a subarray of values. The subarray corresponds to the leaves either contains just a single array element or have multiple array elements, all of which have the same value. Indexing of the line segments of polygons presents new problem. There are extensions of KD trees and quad trees for this class. However, a line segment of polygon may cross a partitioning line. If it does, it has to be split and represented in each of the subtrees in which its pieces occur. Multiple occurrences of a line segment of polygon can result in inefficiencies of storage as well as inefficiencies in querying. Let's next see R trees. A storage structure called an R tree is useful for indexing of objects such as points, line segments, rectangles, and other polygons. An R tree is a balanced tree structure with an indexed object stored in leaf nodes, much like a B plus tree. However, instead of range of values, a rectangular bounding box is associated with each tree node. Supported in many modern database systems along with variants like R plus trees and R asterisk trees. Basic idea is to generalize the notion of one-dimensional interval associated with the B plus tree node to an n-dimensional interval, that is an n-dimensional rectangle. The bounding box of a leaf node is the smallest rectangle parallel to the axis that contains all objects stored in the leaf node. The bounding box of internal nodes is similarly the smallest rectangle parallel to the axis that contains the bounding boxes of its child nodes. The bounding box of an object, such as a polygon, is defined similarly as the smallest rectangle parallel to the axis that contains the object. Each internal node stores the bounding boxes of the child nodes along with the pointers to the child nodes. Each leaf node stores the indexed objects and may optionally store the bounding boxes of the objects. The bounding boxes help speed up checks for overlaps of the rectangles with the indexed objects. If a query rectangle does not overlap with the bounding box of an object, it cannot overlap with the object either. If the indexed objects are rectangles, there is of course no need to store bounding boxes since they are identical to rectangles. The figure shows an example of a set of rectangles drawn with a solid line and the bounding boxes drawn with a dashed line of the nodes of an R tree for the set of rectangles. Note that the bounding boxes are shown with extra space inside them to make them stand out pictorially. In reality, the boxes would be smaller and fit tightly on the boxes that they contain. That is, each side of the bounding box B would touch at least one of the objects of bounding boxes that is contained within B. The R tree itself is at the right side of the figure. The figure refers to the coordinates of bounding box is a PBI in the figure. We shall now see how to implement search, insert, and delete operations on the R tree in the following slides. Let's first see search. As the figure shows, the bounding boxes associated with the sibling nodes may overlap in B plus trees, KD trees, and quadtrees. In contrast, the ranges do not overlap. A search for objects containing a point therefore has to follow all child nodes whose associated bounding boxes contain the point. As a result, multiple paths may have to be searched. Similarly, a query to find all objects that intersects a given object has to go down every node where the associated rectangle intersects with a given object. Now let's see insert. When we insert an object into an R tree, we select a leaf node to hold the object. Ideally, we should pick a leaf node that has space to hold a new entry and whose bounding box contains the bounding box of the object. However, such a node may not exist. Even if it did, finding the node may be very expensive since it is not possible to find it by a single traversal down from the root. At each internal node, we may find multiple children whose bounding boxes contain the bounding box of the object, and each of the children needs to be explored. Therefore, as a heuristic in a traversal from the root, if any of the child nodes has a bounding box containing the bounding box of the object, the R-tree algorithm chooses one of the arbitrarily. If none of the children satisfies this condition, the algorithm chooses a child node whose bounding box has the maximum overlap with the bounding box of the object for containing the traversal. Once the leaf node has been reached, the node is already full. The algorithm performs node splitting and propagates splitting upwards if required in a manner very similar to B plus tree insertion. Just as the B plus tree insertion, the R tree insertion algorithm ensures that the tree remains balanced. Additionally, it ensures that the bounding box of the leaf node as well as internal nodes remain consistent. That is, bounding boxes of the leaves contain all the bounding boxes of the objects stored in the leaf, while the bounding boxes of internal nodes contain all the bounding boxes of the children node. The main difference of the insertion procedure from the B plus tree insertion procedure lies in how the node is split. In a B plus tree, it is possible to find a value such that half the entries are less than the midpoint and half are greater than the value. This property does not generalize beyond one dimension. That is, for more than one dimension, it is not always possible to split the entries into two sets so that their bounding boxes do not overlap. Instead, as a heuristic, the set of entries S can be split into two disjoint sets S1 and S2 so that the bounding boxes of S1 and S2 have the minimum total area. Another heuristic would be to split the entries into the two sets S1 and S2 in such a way that S1 and S2 have minimum overlap. The two nodes resulting from the split would contain the entries in S1 and S2 respectively. The cost of finding splits with minimum total area of overlap can itself be large, so cheaper heuristics such as the quadratic split heuristics are used. Now let's see quadratic split, which divides the entries in a node into two new nodes as follows. First, find pair of entries with maximum separation, that is a pair such that the bounding box of the two would has the maximum wasted space or area of bounding box minus sum of areas of two entries. Next, place these entries in two new nodes and repeatedly find the entry with the maximum preference for one of the two new nodes and assign the entry to that node. Preference of an entry to a node is the increase in area of bounding box if the entry is added to the other node. Then stop when half the entries have been added to one node, then assign remaining entries to the other node. Next, let's see deletion. Deletion can be performed like a B plus tree deletion, borrowing entries from sibling nodes or merging sibling nodes if a node becomes underfull. An alternative approach redistributes all the entries of underfull nodes to sibling nodes, with the aim of improving the clustering of entries in the R tree. The storage efficiency of R trees is better than that of KD trees or quad trees, since an object is stored only once, and we can ensure easily that each node is at least half full. However, querying may be slower, since multiple paths have to be searched. Spatial joins are simpler with quad trees than with R trees, since all quad trees on a region are partitioned in the same manner. However, because of their better storage efficiency and their similarity to B trees, R trees and their variants have proved popular in database systems that support spatial data. This concludes the chapter. We will see you with the multimedia database next time. Thank you for listening.